Okay, so we will start the chapter number 6, Isomorphisms. I'll present the quote by Henry Poincaré that mathematics is the art of giving the same name to different things. Henry Poincaré was in between 1854 to 1912. Okay, so isomorphisms. Let's talk about the motivation. So, suppose we have an American person and a German person, and they are asked to count a handful of objects. The American says 1, 2, 3, 4, 5, and so on, whereas the German says eins, zwei, drei, vier, fünf. Are the two doing this different things? No, they are both counting the objects, but they are using different terminology to do so. Similarly, when one person says 2 plus 3 is 5, and another says 2 und 3 ist 5, the two are in agreement on the concept they are describing, but they are using different terminology to describe the concept. Now, an analogous situation often occurs with groups. The same group is described with different terminology. We have seen that in chapter number 1, we described the symmetries of a square in geometric terms, whereas in chapter 5, we described the same group by way of permutations of the corners. Now, in both cases, the underlying group was the symmetries of a square. Okay. Now, in chapter 4, we observe that when we have a cyclic group of order n generated by A, the operation turns out to be essentially that of addition modulo n. Right? Now, let's write that. So let's say we have a cyclic group Cn of order n generated by A, where A has order n. The operation is addition modulo n. Right? Since A power R, A power S is equal to A power K, where K is nothing but R plus S mod n. Right? So, for example, we take U of 43 and U of 49 is R cyclic of order 42. So each has the form A generated by A, where A power R, A power S is equal to A power R plus S mod 42. In this case, you can say you have 43 and you have 49 are isomorphic with a cyclic group of order 49, sorry, 42. Okay, so we have understood the motivation behind the isomorphisms. Right now, let's talk about definitions and examples. Right. So in this chapter, we give a formal method for determining whether two groups defined in different terms are really the same. When this is the case, we say that there is an isomorphism between two groups. The notion was first introduced by Galileo about 180 years ago. So you can write the notion of isomorphism was first introduced by Galileo about 180 years ago. And the term isomorphism is derived from the Greek word isos, meaning the same or equal. The term isomorphism, I would write it as this one, is derived from the Greek word isos, meaning same or equal. And morph, so words isos meaning same or equal, and morph meaning from, not from, but from. Okay. Now, Alan Bay has colorfully defined an algebraist as a person who can't tell the difference between isomorphic systems. Okay. So let's give you a definition, proper definition, which says, which is a definition of a group isomorphism. Right? Definition says an isomorphism phi from a group G to a group G bar is a one-to-one mapping or you can say it's a function from G to G bar that preserves the group action or the operation, you can say. Group operation, which is, or that is, we can write that phi of AB is going to be equal to phi of A into phi of B for all A comma B in G. If there is an isomorphism, if there is an isomorphism from G to G bar, beta saying on to G bar, we say that G and G bar are isomorphic and write Simps G bar. Okay, this is the definition of a group isomorphism. Right. Now, the definition of isomorphisms ensure that if phi is an isomorphism from G to G bar, then the operation table for G bar can be obtained from the operation table for G by replacing each entry in the table for G by phi of x. By phi of x. Thus the groups differ in the notation only. Now, to say that, so let's say we have a table for G where we have anything here, and say A here, and anything here, and similarly we have B here, right? Now, we don't know about these, but we do know about this is going to be AB, right? Now, similarly, if we write a table for G bar, and that is going to be, we have phi of A here, phi of B here, and then we can write something like, this is going to be phi of AB. So I said every element of G bar, we can replace that by an element of by phi of x. Okay, so that's why we are writing phi of AB, phi of A, and phi of B. Now it is implicit in the definition of isomorphism that isomorphic groups have the same order. You can write that isomorphic groups have the same order. It is also implicit in the definition of isomorphism that the operation on the left side of the equal sign is that of G, whereas the operation on the right side is that of G bar. And there are 4 cases involving the product and addition, which we can show in the table. So let's say we have G operations, then we have G bar operations, okay, and then operation preservation. Okay, so let's say we have multiplication. Again, multiplication, we denote that by dot, and then we have addition, now we have multiplication again, addition, multiplication, addition. Then what will be the operation preservation? So that is going to be phi A dot B here, because that's the operation of G. And over here, we can also write phi of A dot phi of B, because that is going to be the operation of G bar. Similarly, if we have phi of A dot B here is operation of G, then but the operation of G bar is plus, so we write phi of A plus phi of B. Okay. Similarly, we have phi of A plus B, but here it's going to be phi of A into phi of B, right? And if we have addition on both sides, we would just write phi of A plus phi of B. That's how we preserve the operations, right? Perfect. Now there are 4 separate steps involved in proving that a group G is isomorphic to a group G bar. Let's write them. There are 4 separate steps involved in proving that a group G is isomorphic to a group G bar. Let's write the step 1. Step 1. First we check mapping. So we define a candidate for the isomorphism. So we need to give a mapping. Define a candidate for the isomorphism, that is a function, that is define a function phi from G to G bar. Okay. Now, step 2 is one one. We need to check that mapping is 1 1. So prove that phi is 1 to 1. That is, assume phi of A is equal to phi of B, and prove that A is B. Okay. Step 3 says that you need to check onto. Okay. Now you need to prove that phi is onto. Okay. That is, for any element G bar in G bar, small g bar into capital G bar, find an element G in capital G such that phi of G is equal to G bar. That is the step 3. Step 4 is you need to check operation preservation. Okay, so you need to prove that phi is operation preserving. And that is show that phi of AB is equal to phi of A into phi of B for all A comma B in the capital G. Now, if you go back into the mathematics you have learned, none of these steps are actually new to you or unfamiliar to you. The only one that may appear novel is the fourth one. It requires that one be able to obtain the same result by combining two elements and then mapping, or by mapping two elements and then combining them. So roughly speaking, this says that the two processes, operating and mapping, can be done in either order without affecting the results. Okay. Now, the same concept arises in calculus when we say the limit or the integration using the limit. Okay. So you can actually write the same concept of operation preserving arise in calculus when we say that limit x tends to a of f of x dot g of x is going to be equal to limit x tends to a of f of x multiply limit x tends to a g of x. Or you write integral a to b of f plus g dx is equal to integral a to b f dx plus integral a to b g dx. And that is really interesting that you can see this operation preserving thing already arise in calculus. Okay. Now in linear algebra, an invertible linear transformation form a vector space V to a vector space from a vector space V to the vector space W is a group isomorphism from V to W. Every vector space is an abelian group under vector addition. That's again an application in linear algebra. So let's write that also. It's a useful example. So in linear algebra, an invertible linear transformation from a vector space V to a vector space W is a group isomorphism from V to W. Why? Because every vector space is an abelian group under addition. If you take the properties of the vector space, you are actually checking, you are looking at an abelian group sitting inside a vector space. Right. Now let's try to give you some examples. Example 1. Example 1 says, let G be the real numbers under addition and let G bar be the positive real numbers under multiplication. So G be the set of real numbers under addition and G bar be the set of positive real numbers under multiplication. Remember, positive real numbers does not contain 0. Then G to G bar are isomorphic under the mapping. Then phi is a map from G to G bar given by that phi of x is equal to 2 power x. Now certainly, and phi is an isomorphism. Okay. Now certainly phi is a function from G to G bar. So it's a mapping. First step one is done. So let me break those into steps. Maybe that would be helpful because it's a first example. So phi is a function. Step two. One-to-one, right? Now prove that it is one-to-one. Suppose that 2 power x is equal to 2 power y, then log at base 2 of 2 power x is equal to log at base 2 of 2 power y, and therefore you can write x is equal to y. Step 3. Step 3 says you need to check onto. We must find for any positive real number y some real number x such that phi of x is y. So that is 2 power x is equal to y, and solving for x gives you log 2 of y. Solving for x gives you that x is equal to log 2 of y. Right? Finally, step 4. Step 4 says you need to preserve the operation. So the operation is phi of x plus y, because in our first group we have addition operation, in our second group we have multiplication operation. So phi of x plus y is going to be 2 power x plus y, and that we can write as 2 power x into 2 power y. So that is going to be phi of x into phi of y, and it is true for all x and y in G. So phi is indeed an isomorphism. Okay. Now you can, let's talk about the example 2. Example 2 said any infinite cyclic group is isomorphic to Z. Any infinite cyclic group is isomorphic to the state of integers. Indeed, if A is a generator of a cyclic group, so let's say we have a cyclic group C, let's call it, and it is generated by A, then the mapping A power k is going to go to k is an isomorphism. isomorphism. Okay. Now, any finite cyclic group A of order n is isomorphic to Zn. Any finite cyclic group C generated by A of order n is isomorphic to Zn. Zn under the mapping such that phi is a map from Cn to Zn given by that it sends a power k, phi sends a power k to k mod n. Okay, or you can write in different way, or phi of a power k is k mod n. You can write that also. Now, these correspondents are functions and are one-to-one in the sense of theorem 4.1, which we have done already in chapter 4. Obviously, the mappings are also onto that. The mappings are operation preserving follows from the things we have done in chapter 0. Okay, perfect. Now, few more examples. So, example 3. Example 3 says the mapping from R under addition to itself given by, so let's say G is R under addition, G bar is also R under addition, phi is a map from G to G bar given by that phi of x is equal to x cube is not an isomorphism, although phi is one-to-one and onto, but it is not operation preserving. Not operation preserving. Operation preserving. Since you can say phi of x plus y should be x plus y cube, which is not equal to x cube plus y cube. So it is not equal to phi of x plus phi of y. Okay, perfect. I should take this and write it here. Right. Number 4 can be that let's take u of 10 is isomorphic to Z4 and u of 5 is also isomorphic to Z4. Now, to verify this, one need only observe that both u of 10 and u of 5 are cyclic of order 4, and then we can apply example 2 because both u of 10 and u of 5 are cyclic of order 4. So by example 2, it is true. Perfect. Let's write one more example and then we will finish there. Example 5. So there is no isomorphism from Q, the group of rational numbers under addition, to Q star, the group of non-zero rational numbers under multiplication. So let's say we have G, which is Q under addition, and G bar, which is Q star under multiplication. And so there is no isomorphism. There is no isomorphism between G and G bar. If phi were such a mapping, there would be a rational number A such that phi of A is -1. But then -1 can't be written as the product of two numbers. Okay? And that's the lacking point. So you can say if phi were such a mapping, then there would be a rational number A such that phi of A is -1, but then you can write -1 is equal to phi of A, and that you can write is phi of 1/2 A plus phi of 1/2 plus 1/2 of A, and that you can write phi of 1/2 of A into phi of 1/2 of A, and that in you combine using the order preserving thing is phi of 1/2 of A square, right? But the problem is, however, no rational number squared to or is -1. There is no map which can be an isomorphism between G and G bar in this case. Thank you so much. When I say we'll talk about one more example, and then we will talk about the famous Cayley theorem.